Okay, good morning, everyone. Let's get started today's class. So, so we learned about the transistor, the basic of a transistor. So, as I mentioned, the transistor is a very fundamental component which can be used for building our digital systems, right? So we can implement a transistor using semiconductor technology. So and then uh, actually, so you know, so actually we are learning about the hardware. So and then actually the transistor is a very basic device of the hardware system. Okay, so but actually the detailed characteristics of a transistor is a little bit tricky for understanding because so we are familiar with software, right? Software programming languages or some software aspect. So actually we are not familiar with some hardware components underneath of the computer system. But try to understand the basic behavior of a transistor. Okay, so we can understand the basic behavior of a transistor like the switch, right? So I mentioned that actually a transistor is a controllable switch. Okay, it's a controllable switch. And then we can understand that this transistor is composed of three nodes, like drain, source, and gate. And then we can gate the connection and disconnection of this switch, the transistor, using gate. Okay. So just understand some behavior. So if you see the symbol of a transistor, so it looks like this, and then this is drain and source, and then this is gate. So you can understand. So using this gate node, drain and source can be connected. This is the turn on state, or drain and source is disconnected. This is turn off state, like this. So actually, in the previous class, I explained about some semiconductor technology in a transistor, like the p-type semiconductor, p-type silicon or n-type silicon. But so actually, if you want to understand some behavior of the basic gates in some computer chips or computer processors, what is the systems, then just understand this behavior, the basic behavior. It's very similar to some very simplified behavior of a transistor. So we can understand the behavior of a transistor in a digital manner, right? like analog, So if G equals 0, so it's like a digital value. So control signal becomes 0, then it's disconnected. So which means it's turned off. The transistor is turned off. If G is 1, so if the digital value is 1 for the gate node, then the transistor is turned on. So you can understand the behavior of the transistor like this. Okay. So this is the structure of NMOS transistor. Okay. Actually, there are two kinds of transistors: PMOS transistor and NMOS transistor. Okay. And then in the previous class, we learned about the NMOS transistor. Okay. So in the NMOS transistor, so we use the p-type substrate and then n-type silicon for the some drain and source node. So this is called the well. Okay. And then between the two nodes, source and drain nodes, we can use the insulator. It's a silicon dioxide, and then above this insulator, then we can dope. We can dope. So it's called the dope. We can dope polysilicon. Polysilicon is conductor. Okay. So and then gate node is connected to the polysilicon. Okay. So so and then this is the symbol of NMOS transistor. Okay. So if the gate is 0, okay, then we cannot observe channel between source and drain. So using this channel, then the free electron can move in this channel. But if gate is 0, then free electrons cannot move between source and drain. So this is the turn off state. Okay. And then if the gate is 1, so if the gate is the high voltage is given to the gate node, then channel is generated. Then using via this channel, free electrons can move between source and drain. So it's connected. Okay. So this is the behavior of NMOS transistor. NMOS transistor. Okay. Okay. And please check your attendance. Okay. On the blackboard. And then, so we can also define PMOS transistor. So if you see the structure of the PMOS transistor, then what is different? So actually the shape, the figure, the shape is very similar. Okay, so it is composed of a substrate, it's a base, and then two wells. Okay, but what is different? So I believe you can observe the substrate is for the substrate for the PMOS transistor, we use N-type silicon. Okay, so N-type silicon includes more free electrons, and then for the source and drain node, so we use the P-type silicon, right? So there are more holes. There are more holes for the P-type silicon, and then this is the gate. The gate actually the gate is the same. So what is different? The substrate is different, and then the source and node, the drain nodes, source and drain nodes are different. So we can use the P-type silicon for the source and drain nodes, and then we can use N-type silicon for the substrate. Actually, the behavior of this PMOS transistor is different from the behavior of NMOS transistor. Okay, so but we can easily understand the behavior of this NMOS transistor. Okay, so if you see the symbol of a PMOS transistor, so you can find that the symbol is very similar to the NMOS transistor. Only one difference is there is a gate here, and then the gate you can observe bubble. Okay, and then this the system bubble, like this circle, small circle. Bubble represents inverse, right? Inverse. So NMOS transistor. So this is the symbol of the NMOS transistor. Okay, so gate is just connected to the gate is connected directly, but we cannot observe any bubble here. So it means that if G is 1, it's turned on, and then if G is 0, then the MOS transistor is turned off, right? And I mentioned this is the bubble represents inverse. So what does that mean for the PMOS transistor? If the behavior is inverse of the NMOS transistor, so which means if the G is 0, okay, the inverse, so it's the transistor is off. Oh, no, transistor is on, okay, right? Because it's a PMOS, and then there is a bubble here. And if the G is 1, it's off. Okay. So actually, so we can easily understand if we can understand some basic behavior of NMOS transistor, then I believe we can also understand the behavior of a PMOS transistor. So actually, so it's just the inverse, okay? So this is the PMOS transistor. Uh, so this is the summary of the transistor function, right? So this is the symbol of the NMOS transistor, and the gate. So gate is directly connected to this node, okay? So for the NMOS transistor, and then if the G is 0, so if the gate voltage is low or ground, then the transistor is the drain and source are disconnected. See, this is the off state. And if the G is 1, then drain and source are connected, then this is on state. And the PMOS is inverse, so you can find bubble here. So if the G is 0, it's a ground voltage is given to the gate node, then transistor is turned on. PMOS transistor is turned on. So drain and source are connected. And then if the G is 1, is a high voltage is given, then drain and source are disconnected. So you can just understand this behavior. And then based on this property, we can build a CMOS circuit. So I mentioned NMOS and then PMOS, and then now I mentioned CMOS. What is this MOS? Okay. So this is the basic structure of CMOS. CMOS circuit. So why is it called C? So C represent complementary. Okay. So so complementary. So CMOS represent the complementary MOS transistor. So which means by using both PMOS transistors and NMOS transistors, then we can build a circuit, the transistor circuit. Okay, so which means that we require both NMOS transistors and PMOS transistors to build a circuit, okay, a digital circuit. And then this circuit is called CMOS circuit. Okay, that's so that you can see this is the CMOS transistor. So CMOS means just NMOS plus PMOS. So why? Why we need to use both PMOS transistors and then NMOS transistors for building an electric circuit, well, most transistor circuit. So actually, in the previous slide, I just mentioned that, so we can understand the behavior of a transistor in a digital manner. So it's simplified approach. Okay, but actually, so we need so in the real behavior of a transistor is analog. So it means that So actually, the voltage level is changed continuously. Level is changed continuously. But we just mentioned that MOS is we can just understand the MOS transistor and the PMOS transistor like some digitally working switch, but actually in the real world it's not true. So you can find some property like here. NMOS transistor is has good zeros. So what does that mean? So it's a switch, okay? It's a MOS transistor switch, okay? So because this is a switch, then we can just think that A and B are just connected. So which means that the signal for this A is delivered to the node B. Right. So this is the switch. So and then A has the some voltage level, right? So we just define the value of the this circuit using the voltage level. So the connected means that the voltage level of A is delivered to the another node B, but so which means that the voltage level of B becomes equal to the voltage level of A. Okay. So actually the real world, so actually the voltage level is changed in the circuit. Then so if a certain information or if a certain data is transferred, so which means that actually the voltage level is changed between two nodes. Okay. So it may be difficult. It may be tricky for understanding, but it's true actually in the real world. So we can understand. We can just understand that if the MOS transistor, the value of A is delivered to the value of B if MOS transistor is turned on. So which means that the gate becomes 1, then the data of the value of A is transferred to the B. But problem is that if the A value is the ground, okay, so it's a low voltage, then B can be also ground clearly. So do you understand? So A is the voltage level of A is low, so it's ground level, and the gate becomes 1. So which means that the B is connected to the A. So in this case, the value at this node A is delivered to the node B. But if the A is a 0, then B becomes 0 clearly. Okay? But how? But however, if A is the high voltage, then B cannot become high voltage like VDD clearly. Okay, so NMOS and for the NMOS transistor, so if the driver is 0, so which means that this is the driver, so which means that the data is given to this node A, it drives, but if the A is 0, low voltage, then B becomes 0 clearly for the turn on state. But if A is the high voltage, then B cannot become high voltage clearly. So that's the problem. So this is some analog property, analog characteristics of NMOS transistor. So even though we can understand, so it's fine. So we can understand the behavior of the NMOS transistors and then PMOS transistor in a digital manner, that's fine. Okay, so because we are digital guys, so, okay. But in the real world, if we just analyze very detailed behavior of a transistor, then transistor has this property. And most is a good for is a good has switch for value 0, but if the driver is it means that the A node is high voltage in the high voltage, but this value cannot be delivered to the other node. Okay, so that's the problem. PMOS, the inverse, the behavior of PMOS transistor is the opposite of NMOS transistor. Okay, so for the PMOS transistor, so we can use the PMOS transistor like a switch, right? But PMOS transistor is the pass good once. Okay, so which means that this for the PMOS transistor, the PMOS transistor is turned on. Then if the A has the high voltage, A is in the high voltage level, then this value, this high voltage can be delivered to the other node B, okay? But it's clearly, but if the A is the low voltage, the ground level, then B cannot be ground level clearly. So we use these PMOS transistors and the NMOS transistors complementarily. Okay, so complementary means that so we need to use some good behavior, so advantage of certain component selectively. Okay, so that's why we just combine PMOS transistor and then NMOS transistor to build a circuit. Okay, so the stable digital circuit, and then this is called the CMOS transistor circuit. Okay, so usually for the digital circuit, when we build a digital circuit, we use both PMOS transistors and NMOS transistor. Okay, so you can find the input is here, right? So actually the input value is connected to the gates. Gate nodes of PMOS transistors and NMOS transistors. So using these input signals, we can control the behavior of transistors, right? So based on the input, then we can generate different outputs logically, right? And deterministically, then we can build a logic circuit, right? Do you understand? So think like a certain function, okay? So certain function is that this is input and this is output, and then a certain function can generate some deterministic output based on input signal. Then we can generate a logic, right? It's the same. So why can we build a logic using transistors? Because based on the input, then we can control the deterministic behavior of transistors. Okay, that's why we can use transistors for building logic circuit. Okay, so anyway, input signals are connected to gate nodes of transistors, which means that input signals are connected to the gate nodes of PMOS transistors. Also, the input signals are connected to the gate nodes of NMOS transistor. So, and then you can find some new terminology like the pull-up network. It's a pull-up and pull-down network. So how can you understand this network? So actually, so it's kind of some electric circuit analogy. Okay? So we can understand that in the output node, there is a capacitor. So capacitor. So what is a capacitor? What is a capacitor? We can store electrons. Okay, actually we can store electric charges. Okay, with charges. Actually, though we can the free electrons move in a conductor or circuit, but we can just understand that this is the electrons are charges, right? Charges. So in a capacitor, we can store charges, electric charges, right? So capacitor, right? Capacitor. That means just some storage, right? Storage. Then how? But then I mentioned that this is the output. So which means the output can become this. This is the digital circuit. So output can become high voltage, right? High voltage or low voltage. And what is the high voltage? High voltage is the VDD, and then low voltage is the ground, right? Do you understand? You understand? Then how can we make high voltage to this output node? So the circuit looks like this, right? So this is the capacitor. Okay. So if we store many positive charges in the capacitor for this plane, then we can make high voltage to this output node. Do you understand? Huh? So this is the capacitor, okay? So capacitor. And then we can store charges here, okay? Like plus charge is a positive charge. And then the other plane of the capacitor, the minus charge is stored. So which means in the capacitor, this node becomes the high voltage, right? Because there are many positive charges, right? Do you understand? So it's saying there is a capacitor here. So actually this is not a real capacitor, it's a parasitic capacitor. Okay. But if we store positive charges in this capacitor, like this at this plane, then we can make output voltage high. Right? Then how? So you can find the VDD is here. Okay. So this is the VDD. So another node of the PMOS transistor is connected to the VDD. And then, so the input is connected to the gate, right? Gate of the PMOS transistor. So this VDD is connected to the output node, right? Output node. Then we can store positive charge to this capacitor, right? So that's why this network is the full of network. So which means that using the PMOS transistor, we can make the voltage level of the output high if this full of network is turned on. Okay, that's why the PMOS transistor is called we can make full up network. So make the voltage up. Okay, it's a high voltage. So this is called the full up network. So inversely, so this is also a capacitor. So this is the pull down network. So which means that uh, we can just expect that this is the using the NMOS transistor, then we can make the voltage level of output low. How? So you know this is the ground. So another node of the NMOS transistor is connected to the ground. Okay, and then if this output node is connected to the ground, then charge is actually dissipated. So it means that this output becomes less. Output node includes less positive charges. So the positive charge is dissipated, so it becomes ground. It's a low voltage. So this is why the NMOS transistor is called. So we can build NMOS transistor. We can build pull down network using NMOS transistors. So because if the NMOS transistor is turned on, then this capacitor is connected to the ground. So positive charge is dissipated, so it's reduced, then output becomes ground, so low voltage. So by combining the NMOS transistor and then PMOS transistor, we can build this circuit, the pull up network and then pull down network, and then we can control the output using input signals. Okay, so that's why we require both PMOS transistors and then NMOS transistors for building digital circuit. So it's called the CMOS circuit, complementary MOS circuit. Okay. Okay. Then by applying this knowledge, then we can implement basic logic gate. So in the previous classes, we learned about the basic logic gate. So what are basic logic gate? Not, okay, not buffer and or exclusive or, right? And then NAND, door, and then exclusive door. Okay. So these are basic gates we learned in the previous class, right? So, and then why are we learning about the transistors? It is because using transistors, we can build basic logic gates. Okay. Okay, let's see how. So this is a NOT gate. So I hope everyone knows NOT gate, right? So it's just very simple. So this is the input node, input signal A, and then this Y is the output node, and then this is a symbol of a NOT gate. And then so this is the Boolean equation of a NOT gate. Okay, and then we already know the behavior of a NOT gate. So if the input is 0, 0 means low voltage, okay, low voltage, and then Y becomes 1, the high voltage. If the A is 1, the high voltage, then output Y becomes low voltage. Okay. Then how can we build this NOT gate? So NOT gate is the basic CMOS circuit, right? So this is a figure of CMOS circuit for NOT gate. then how can we understand the behavior of this CMOS circuit? Okay, so you can just map the symbol of this NAND gate to this real CMOS circuit. So if you see so this is A, the input value, input signal. So A is here. So this is the input port or input node of NAND gate. And then where is the Y? Y is here. Okay. Then as you can see, Y is here. Okay. So if we just give a certain value or certain voltage level to the input of NAND gate, so A, then the output value is decided. Then how? So let us assume that A is 0. Okay, the firstly A is 0, so which means A is the actually ground. It's a ground, low voltage level. Okay, then so this is 0, and then this 0 is connected to the gate of PMOS transistor. It's a P1, and then gate of NMOS transistor. Then this is 0. Then P1 is turned on. Okay, so like this. So for the PMOS transistor, if the gate is 0, then it's turned on, right? And then the same value 0 is connected to the NMOS transistor. How about the NMOS transistor? It's off, right? Then what will happen? So as I mentioned, so this is the capacitor actually. So this is Y. So this is on, this is off. Okay, so which means this disconnected. The NMOS is disconnected. So which means that the output Y is disconnected from ground. Okay, so okay, and then the PMOS is on, right? So PMOS is connected. So which means the Y is connected to the VDD. Okay, the high voltage. And then so this is the supply voltage. Okay, high VDD. So actually, so which means that we can drive the output Y using VDD and ground. Okay, so in this state, the output Y is connected to the VDD. Then also I mentioned that the P1 is the good one pass. Okay, high voltage is easily passed to the Y. Okay, delivered to the output Y. So Y is the 1. It's high voltage. Okay, do you understand? And then inversely, so if the A becomes 1, so it's the VDD, the high voltage. P1, so 1 is connected to the gate of the PMOS transistor. So this is off. Okay, it's a bubble. Okay, and then the NMOS transistor is on, right? So in this case, because the PMOS transistor is off, so this is disconnected. The PMOS is disconnected, but NMOS is connected to the ground. So Y is connected to the ground. So this is 0 because this is low and ground. Right? So actually, based on this knowledge, then we can estimate the behavior of CMOS circuit, okay, and PMOS transistor and NMOS transistor, and then we can figure out the output value based on the input value. So this is a NOT gate. So it's a very basic logic gate. So which means that using a CMOS circuit, using PMOS transistor and NMOS transistor, we can make basic logic gate. It's a NOT gate. Do you understand? Okay. Okay. How about the NAND? Okay, so this is the NAND gate has two input signals, two input node, and then one output node. And then so this is the symbol of the NAND gate symbol. Okay, so it's an and bubble, right? It's an inversed. And is inversed. So this is Boolean equation, and then this is the truth table of NAND gate, right? Then this is the CMOS circuit of NAND gate. Okay, so it's a little bit more complex, right? Because the NAND gate includes two PMOS transistors and two NMOS transistors, right? So as you can see, so there are two inputs, A and B. So A is mapped to this input A, and the B is mapped to this node. Okay, and then the A is connected to the two PMOS transistors, and the A is connected to the PMOS transistor P1 here. So this is A, this is A. Okay, P1 and N1, and node B, another input B is connected to the N2 and the P2. Okay. Okay. This is the output Y. And then, this is the NAND gate, and then you can find that, PMOS transistors are connected to VDD, high voltage, in parallel, right? So P1 and P2 is connected to the VDD in parallel, and then NMOS transistors are serially connected to the ground. Okay. Then let's see the behavior of this NAND circuit. So A is 0 and B is 0. Then P1 or AP1 is on, right? Because the A is connected to P1 and N1. Okay. And then how about the P2? B is connected to P2. So this is also on because the B is 0. How about the N1? Obviously off. Okay. Then in this circuit, this is on, and N1 and N2 is off. So Y is connected to the VDD, right? So this is 1. So we can easily check the other transistors. So 0, 1, this is on, but this is off. And then N1 is off because it's 0, and 2 is on, right? Then what will happen? So in this case, the P2 is off. Okay, the P2 is off. It's off, disconnected, and where is the N1? N1 is disconnected, right? But for the Y, output node Y, P1 is connected, so Y is connected to the VDD. Okay? And then, the MOS transistors are serially connected to the ground, but one of the MOS transistors is disconnected, so Y is disconnected from ground. So what is Y? Y is 1. It's VDD. Okay, do you understand? Okay, so let's see the behavior of other transistor. So this is off, this is on, this is on, this is off, because inverse. Okay, then what will happen? Oh, in this case, P1 is disconnected, but P2 is connected, so it's 1, right? And then in this case, 1, 1, obviously off, on. So disconnected is connected, but Y is connected to the ground because N1 and N2 are both turned on. Okay. So what happened? Oh, because Y is connected to the ground. So this is 0, the ground. So if you see this table, so you can find that, this is input and this is output. So actually the result of this table is equivalent to the truth table of NAND gate, right? So this is A, B, and this is Y, so Y. Okay, so we can build NAND gate was like this, okay, using two MOS transistors and then two PMOS transistors. So we can build a NAND gate, okay? Okay, so this is the thing. Then how can we build three input NOR gate? Actually, it's the same, three input NOR, but if we see this circuit, like this circuit, so we build a NAND, right? Right? But actually, so think about also on a switch, okay? So if switch is connected serially serially, then it's actually this is the representer. Serially connected, this is actually AND, right? Because if switches are serially connected, if one of the switches is turned off, then this A and B are disconnected. And switch is connected to in parallel, right? In parallel, then this is actually meaning of OR, right? So what can you find actually? So this is the NAND. For the NAND circuit, NMOS transistors are serially connected. And then PMOS transistors are connected in parallel. Okay? The different. And then, this is the pull down network, the pull down. So if the NMOS transistors are turned on, so it's connected to the ground, then the output Y is connected to the ground, so Y becomes the 0. Okay, so this is the AND, but if this circuit, this network is activated, it's turned on, then y becomes 0, right? 0. So it's NAND. Still the same? So I mentioned that, oh, this is the meaning of serially connection. Serially connection is AND, right? But for the MOS transistor, so if these MOS transistors are activated, so the pull down network is activated, then Y becomes 0. So actually NAND. How about the PMOS transistor? It's a parallelly connected, but it's if the one of these PMOS transistors is activated, it's turned on, then it's connect Y becomes 1. Okay? So we can understand. So NMOS transistor makes the output 0. So if the NMOS transistor is activated, the NMOS transistors are activated. So which means that this NMOS pull down network is activated or enabled when turned on, output becomes 0. On the other hand, if the PMOS pull-up net, this is the PMOS pull-up network. So PMOS pull-up network is activated, then output becomes 1. Okay, so we can understand like this. Okay, then how about the node? It's a 3 input. So this is, so as you can see, this is N, it's a NAP plus 1. Okay. So in the previous example, so this is NAND gate, and then serially connected MOS transistor. So I mentioned that this is the AND. This is, if this is activated, then Y becomes 0. So this is, so it's NAND. With the same approach, this is NOR. Then how can we build a CMOS circuit? This is NOR, or is the is a parallelly connected, but this is not. So from the ground, this is Y, and then this is A, this is B, this is C. So what is this? So I just made pull down network using NMOS transistors, right? But this is OR. So, and then I just connected these 3 NMOS transistors in parallel. So another node of the NMOS transistor is connected to the ground, right? And then NMOS transistors are connected in parallel, okay? Because this is OR and not OR. So which means, if one of this NMOS transistor is activated, so it's enabled, then Y becomes 0. So we can understand the CMOS circuit like this, okay? So this is, if the gate is not NAND, okay, nor, okay, but so it is not NAND nor, so output is the inverse of the input, then actually we can build this circuit using the NMOS pull down network like this. Okay, so it's a NAND, so it's a serially connected or connected in parallel, right? Now how about the PMOS pull up network? So PMOS is actually the opposite of the NMOS transistor. So which means we need to connect the PMOS transistor, opposite manner. So which means PMOS transistors need to be connected in serial, right? And A, B, C, like this. You understand? So this is because the pull down network is activated, then output it becomes 0. So that's why. So this is NOR. So which means you can just make this NOR using the NMOS transistors. So OR is mapped to the parallel structure, the parallel connections of NMOS transistor. So which means that for the Y, so we can make Y 0 using the parallel connections of NMOS transistors. Okay, parallel. So it's a OR, but because net, so this is NOR. And then the topology. So structure of PMOS transistor, the topology of PMOS transistors are the topology of PMOS transistor is inverse of the topology of NMOS transistor. So which means this is serial. Okay, we can connect the PMOS transistor like this. Okay. So I hope you can understand this. Okay. So this is, as I mentioned, so this is the NOR circuit, 3-input NOR circuit. Okay. And how about the AND2 gate? So until now, so I just showed the NOT gate, NAND gate, and then 3-input NOR. So what are common part? What is a common part for these 3 gates? Common part is the NOT. Okay, NOT, NAND, NOR. So it's a kind of some inversion of the result, right? Then how about the AND2 gate? Then how can we build AND gate, AND2 gate? So AND gate. So actually, in order to implement the AND2 gate, we need to make the circuit like this. So but this is not good. So if we just understand the behavior of the MOS transistors in a digital manner, then this can be possible. But in the real world, this is not possible. So as I mentioned, NMOS transistor is a passcode 0. And then PMOS transistor is a passcode 1. That's why PMOS transistor is connected to the VDD, the high voltage, and then NMOS transistor is connected to the ground. But what is wrong for this circuit? I used the NMOS transistor, but this NMOS transistor is connected to the VDD, right? So and then this is not possible. So in a digital manner, this can be possible, but in the real world, in the analog manner, in the analog circuit, this is not possible. So we cannot build. So that's why PMOS transistor. So we need to make two network using PMOS transistors only, and then we need to make pull down network using NMOS transistors only, right? This is not possible. Okay? Then how can we build AND gate? So actually we need to combine NAND plus NAND. Okay? So like this. So in order to build AND gate using CMOS circuit, then we need to firstly build NAND gate first, and then the output of NAND gate is connected to the input of NAND gate. So here, so and then Y becomes this becomes the AND gate. Okay, so we cannot directly build AND gate using a CMOS circuit, right? So we need to build AND gate using NAND gate plus NAND. Okay, then what's the problem actually? So for this NAND gate, we require two PMOS transistors and then two NMOS transistors, right? And then for this NOT gate, we require one PMOS transistor and one NMOS transistor. So actually, in order to build AND gate, we require totally three PMOS and three NMOS transistors. But if we want to build the NAND gate, then we just require two PMOS transistors and then two NMOS transistors. Then what's the problem? Problem is cost. Okay. So if we just use more transistors to build a certain circuit, then this circuit takes higher cost, right? And the cost is very important because so you are engineering student, right? So actually the goal of engineering is to increase the performance and decrease the cost. But if we just increase the cost, it's not good. So actually, so because of this property, okay, we cannot directly connect the NMOS transistor to the high voltage, the VDD. So actually, in order to build the AND gate, we require three transistors, six transistors, six transistors, okay? The three PMOS and then three NMOS transistors, right? So, and then for the NAND gate requires four transistors. So actually the NAND gate and AND gate both are basic gates, but the performance is different. Also, the cost is different. So that's why we need to learn how to optimize circuit. Okay. And the gate, we cannot directly build the gate. So actually, and we need to build AND gate like this. And then, so another basic gate is the transmission gate. So it's a transmission. Okay. So it's just actually you can understand the transmission gate is the switch. Okay. Then you can be you can be some like this. So actually, I mentioned that MOS transistors and MOS transistor is a controllable switch. So you can easily think that so if we want to make a switch, then you can think that we can implement a switch, controllable switch like this. A is here, and then this is the some switch, control signal, and then B is here, and that's it. So we may think like this, but problem is this property. So MOS has ones fully, and then PMOS has zeros fully. And what's the problem? So this is the switch, okay? And then if the S becomes 1, then switch is connected, okay? It's turned on. So which means the A can be 0, A can be 1. So if A is 0, then B becomes 0. And then if A is 1, it needs to become 1. So this is the definition of a switch, okay? So if the switch is turned on, and then if S is becomes 0, then it's disconnected, okay? But what's the problem? The problem is that actually MOS pass once fully. So this is okay. So we can implement this. If A is 0, then B becomes 0 if S is 1. But the problem is that if A is the 1, if data of A is 1, high voltage, B, I don't know. Okay, B should be 1. It needs to be high voltage, but actually we cannot know, we don't know the exact value of B. It is because of this, and not pass once poorly. Okay, so that's the problem. So actually we need to use the PMOS transistor also. Okay, so actually instead of using MOS transistor only, so actually we need to connect the PMOS transistor here and PMOS transistor here, and then actually S is S bar. S bar is connected to the gate of PMOS transistor. So if S equals 0, then it's disconnected, and then you know this is the S bar, so it's the inverse of S. So PMOS transistor is also O. So what is this state? This state is that this is disconnected, right? Do you understand? But if S equals 1, then MOS transistor is connected, and then PMOS transistor is also connected. But because of MOS, the MOS can pass 0 clearly. So which means that if the A is 0, then B becomes 0 clearly. And then if A is 1, then A is connected to the B via this PMOS transistor. So B becomes 1 clearly. So this is a transmission gate. Okay, so this is pure switch, right? Okay, so we can build switch using a transmission gate. And then actually we need to know MOS for the MOS transistor, or MOS transistor pass ones fully, and then PMOS transistor pass zeros fully. Okay, so this is another gate, so another basic gate, transmission gate. Okay. Okay, so we have 5 minutes. And then so let's think about some other cost, power consumption. What is power consumption? So as I mentioned, the power is the IV. So current multiplied by voltage. This is the power. But so but actually if there are some electric component like the capacitance or inductance or resistance, that we can define the power consumption with the other ways. Okay, but what is power? Power is the energy consumed per unit time. So this actually we are very familiar with the energy, right? So which means that if the power is integrated for the some time, this is the energy actually. So which means that like this light. So if we just turn on the light, then the energy is consumed by time. Okay, then power is just the energy consumed per unit time. Then power is also very critical cost in the circuit. Why? We need to pay money. We need to pay money for consumed power, consumed electric power, right? So which means that we need to save power consumption in our house. So in our house, right? So power is also very critical because we need to pay money for consumed power. And then there are two kinds of power consumption actually in a circuit. So it's a dynamic power consumption and then static power consumption. Okay. So it's another some equation. So dynamic power consumption. Dynamic power consumption means that if so actually we learned about the this circuit. So A is connected and then so this is the Y and then this is the NMOS pull down NMOS transistor and then this is the pull up PMOS transistor and then this is A. Okay. So dynamic power means that actually when the this PMOS transistor is turned on, okay, turned on, then charge is stored in the capacitor. And then NMOS transistor is turned on, the charge is dissipated from capacitor. So what does that mean? Output value of this CMOS circuit can be changed, right? When this value is changed, then actually the charges move. Charges transferred from the VDD to the capacitor, and charges are also moved from capacitor to ground. Charges move, power is consumed. 맞잖아요? So, right? The charge moves, power is consumed. So dynamic power means that when the input and output values are changed, then power is consumed in a circuit, and then this power consumption is defined as the dynamic power consumption. And then this is the equation of the dynamic power consumption. So if we see that this equation, the alpha means the activity factor, okay? So activity factor, and then C is the capacitance, B is the supply voltage, F is the frequency. So actually, so we need to learn about the sequential logic later. So which means that I expect that you are not familiar with the frequency, the clock frequency. But just to remember that, so in this time, just to understand that the dynamic power, if the signal values are changed, then the power is consumed dynamically. So this is the dynamic power consumption of a circuit. Static, even though the circuit does not work, so it means that the circuit values are not changed, the power can be consumed. So it is because in this network, actually in the very short time, the P is turned on, P can be turned on, and the N can be turned on. So in this case, this VDD is connected to the ground in a very short time. And then another issue is the transistors are not perfect. So which means that even though the transistors is turned off, it's disconnected, the current, the small current can flow via drain, between drain and source. Okay, so which means that very small current can flow between drain and source, even though the transistor is turned off. Yeah. So static power means that even though the signals, input and output signals are not changed, the small current flow in the transistor through the transistor, then power is consumed. So this is the definition of static power. Okay, so dynamic power is proportional to the activity factor, which means that signal values are changed, then the powers are consumed dynamically. Static power, if the circuit is working, but regardless of the some change of input and output values, the power is consumed. So this is the static power. Okay. Okay, so I will stop here. Any questions? Thank you for your listening and see you in the next class. 감사합니다.